So in continuation with our discussion on mechanical waves, we will learn about standing waves on a string and normal modes of a string. So a standing wave is produced by two trains of waves traveling in opposite direction. It doesn't appear to be moving in either direction of the medium. And by the principle of superposition, the amplitude of the standing wave is the algebraic sum of the instantaneous amplitudes of the individual waves. So in standing waves, we can see points that never move at all. These points are called node. So these are the locations of the node. For this example, this is an example of a standing wave pattern. So these are examples of nodes. So these are points wherein total destructive interference occurs. So this is a node, this one is also a node, and also this one. At a node, the displacement of two waves always equal and opposite and cancel each other out. And midway between the nodes are the points of greatest amplitude. So as you can see, so midway between two nodes are points which has greatest amplitude, and we call this the antinodes. So at this point, total constructive interference occurs. At the antinode, the displacement of two identical waves gives a large resultant displacement. Now consider an incident wave traveling to the right with a wave function, um, say for example y of xt is equal to a cosine kx minus omega t. So this is a wave that is moving, an incident wave that is moving to the right with um, at time t equals 0 and at x equals 0, the displacement of the particle of the medium is at its upward maximum. So this is, we call this the incident wave. Incident wave. So the reflected wave will be y of xt is equal to negative a cosine kx. This time the reflected wave is moving in the opposite direction, so we have a positive omega t term. So this is the reflected wave. Now if these two waves interfere, they will form a standing wave pattern. Note that the change of sign corresponds to the phase shift of 180 degrees or pi radians. So these two waves interfere, and the result of their superposition is the sum of their wave functions. So according to the principle of superposition, the wave y of xt, so we can call this y sub 1, this one is y sub 2, is just equal to y sub 1 plus y sub 2, or simply the algebraic sum of the individual waves. So let us substitute y sub 1. So we have a cosine kx minus omega t plus negative a cosine kx plus omega t. And we can take a out. So we have cosine kx minus omega t minus cosine kx plus omega t. Okay, now we make use of this identity. So we have cosine of two angles, alpha plus beta. This is equal to cosine alpha, cosine beta, minus sine alpha, sine beta. And we also have cosine of alpha minus beta is equal to cosine alpha, cosine beta plus sine alpha, sine beta. Making use of the identities that we had in the previous slide. So we have y of xt is equal to a multiplied by cosine kx, cosine omega t plus sine kx, sine omega t. And then we have minus cosine kx cosine omega t plus sine kx sine omega t. Okay, so we can simplify this. This will be cancelled out. So we are left with a, and then we have sine kx sine omega t, sine another sine kx sine omega t. So we have 2 sine kx sine omega t, or this is equal to 2a sine kx sine omega t. So this is now the wave function for our standing wave pattern. Okay, now we call this one 2a as the amplitude of the standing wave, which is equal to 2 times the amplitude of the individual waves. Okay, so take note that this is the wave function of the standing wave that is produced by the interference of two cosine waves. Now notice that the amplitude of the standing wave is twice the amplitude of either of the original traveling wave. And in order to find the positions of the nodes, so we can set sine kx in this equation equal to 0 to give a 0 displacement. This means that kx is equal to n pi, where n is equal to 0, 1, 2, 3, and so on. Okay, so here the position of the nodes is at n pi over k. So where n is again equal to 0, 1, 2, 3, and so on. So these are the locations of the nodes. Now we have to take note that unlike a traveling wave, standing wave doesn't transfer energy from one end to the other. We can also find the location of the antinodes. So from our wave function for standing wave, we have to set sine kx to be equal to 1. Now this is only true when kx is equal to n pi over 2, where n is equal to 1, 3, 5, 7, and so on, odd numbers. Or we have x is equal to n pi over 2k, where n equals 1, 3, 5, 7, and so on. Okay, so these are the locations of the displacement antinode. Now let us proceed to the normal modes of a string. When there are two boundary points or surfaces, such as that of a guitar string, we get repeated reflections. In such situation, we find that sinusoidal waves can occur only for certain special frequencies, which are determined by the properties of the medium. So let us consider a string fixed at both ends. If it is bowed, a transverse, if it is disturbed, a transverse disturbance will travel to both ends where reflections will occur. So for example, if you have a guitar string and you will disturb it, a transverse disturbance will travel to both ends where reflections will occur. Displacement nodes will be formed at both ends and at every half wavelength. We can satisfy this condition by adjusting the string length to fit an integral number of half wavelengths, or by setting up a particular wave whose half wavelengths will fit into the fixed length of the string. This standing wave can exist only if its wavelength satisfies this. So we have L equals N multiplied by the wavelength over 2, where N equals 1, 2, 3, and so on. L here is the length of the string, lambda is the wavelength, and N here is equal to 1, 2, 3, and so on. So from this equation, we can see that lambda sub n is equal to 2L over n. And the corresponding frequencies can be obtained by substituting our value of lambda. So we have V is equal to lambda times F, and the frequency is equal to V over lambda. So from these equations, we have F sub n is equal to V over lambda sub n, where lambda is equal to this equation. So therefore, F sub n is equal to V times n divided by 2L, where n is equal to 1, 2, 3, and so on. So each frequency, so we have a series of values or frequencies. For example, we have F sub 1 equals V over 2L, F sub 2 is equal to V over L, F sub 3 is equal to 3V over 2L. So each frequency and its associated vibration pattern are called normal modes. Fundamental frequency is the smallest frequency. So this corresponds to n is equal to 1. So we have f sub 1 is equal to v over 2L. Or we can write it as 1 over 2L times the value of v in terms of the tension and the mass per unit length. So this is also called the first harmonic. Okay, and then we also have the second harmonic, and oftentimes it is called the first overtone. This corresponds to n equals 2. Therefore, we have f sub 2 is equal to 2v over 2l, or this is just equal to v over l. Or in terms of the tension and the mass per unit length, we have 1 over L multiplied by the square root of the tension divided by the mass per unit length. And then we can have the third harmonic. This is called the second overtone, which corresponds to n equals 3. So we have f sub 3 is equal to 3v over 2L, which is equal to 3 over 2L times the square root of f sub t over mu. Now take note that in general, your f sub n is just equal to n multiplied by the fundamental frequency. Okay, in terms of lambda, we have this one, the fundamental which corresponds to n equals 1. We have lambda 1 is equal to 2L. For the second harmonic, n equals 2, we have lambda sub 2 is just equal to the length of the string. For the third harmonic, n equals 3, we have lambda sub 3 equals 2/3 of the length. And then we have fourth harmonic corresponding to n equals 4. Lambda sub 4 is equal to 1/2 of the length. And then we have the fifth harmonic, n equals 5. So that lambda sub 5 equals 2/5 L, and so on. So take note of this illustration. So this corresponds to the fundamental frequency, the second harmonic or the first overtone, the third harmonic or the second overtone, the fourth harmonic and the fifth harmonic, and so on. Now notice that at the fundamental frequency, we have 2 nodes and 1 antinode. For the second harmonic, we have 3 nodes and 2 antinodes. For the third harmonic, we have 4 nodes and then we have 3 antinodes, and so on. Okay, so let's have these work examples. With what tension must a rope with length 2.5 meters and mass 0.12 kilogram be stretched for transverse waves of frequency 40 Hz to have a wavelength of 0.75 meter? So, for this problem, we are given with the length, which is equal to 2.5 meters, and then we have the mass, which is equal to 0.12 kilogram. And then we are also given with the frequency, which is equal to 40 hertz, and the wavelength, which is equal to 0.75 meter. Now, the equations that we know, for the equations that we know, we have V is equal to the square root of the tension divided by the mass per unit length. And we also have this equation for V, lambda F, and we also have mu is equal to mass divided by L. Okay, so we are asked to find the tension. So we have V is equal to the square root of F sub t over mu equals lambda times F, where mu is equal to the mass. We have 0.12 kilogram divided by 2.5 meter. So we have mu is equal to 0.048 kilogram per meter. Okay, so from these relationships, we can get F sub t. So we have F sub t is equal to mu times lambda squared F squared. Substituting all the values, we have 0.048 kilogram per meter multiplied by the given wavelength, which is 0.75 meter. We have square, and then we have the frequency, which is 40 hertz. So the tension is equal to 43.2. The unit is kilogram meter per second squared, or that is equivalent to Newton. So 43.2 newtons is the tension. Okay, so the next problem, we have a simple harmonic oscillator at the point x equals 0, which generates a wave on a rope. The oscillator operates at a frequency of 40 Hz and with an amplitude of 3 centimeters. The rope has a linear mass density of 50 grams per meter and is stretched with a tension of 5 newtons. We have to determine the speed of the wave, the wavelength. We have to find the wavelength, and then so we have to write the wave function y of xt for the wave, assuming that the oscillator has its maximum upward displacement at time t equals 0. And lastly is to find the maximum transverse acceleration of points on the rope. Okay, so in this problem, first we are given with a frequency which is equal to 40 Hz, and then we have the amplitude which is equal to 3 centimeters. This is equal to 3.00 times 10 to the minus 2 meters. And then we also have the mass per unit length, which is equal to 50 grams per meter. This is equivalent to 50 times 10 to the minus 3 kilogram per meter in standard unit. And then we have the tension F sub t, which is equal to 5 newtons. Okay, so first we have to calculate for the speed. So we have to find the speed. Now we can use this equation. V is equal to the square root of F sub t over mu, since both F sub t and mu are given. So we have the square root of 5 newtons divided by mu, which is 50 times 10 to the minus 3 kilogram per meter. Okay? So V is equal to 10 meters per second. So next is to calculate for the wavelength. So the wavelength, lambda, is just equal to V over the frequency. So we now have obtained the value of the wavelength, which is 10 meters per second, and then we are given with the frequency, which is 40 hertz. So we have wavelength is equal to 0.25 meter. And then for letter C, we have to find the wave function of the wave. So since it is assumed that the wave is at its maximum upward displacement at time t equals 0, then it must be a cosine function. So therefore, we have y of xt is equal to a cosine, we have kx minus omega t. So we are given with the amplitude. The amplitude is 3 times 10 to the minus 2 meter. We have cosine. Our k is not given, but we can obtain it by, we have this equation, 2 pi over lambda x minus omega is also not given, but we can write it as 2 pi f times t. So we can actually get the value of k and omega, or we can just write it as this, 3 times 10 to the minus 2 meter cosine. We can take 2 pi out, and then in the parenthesis we have x over lambda, which is 0.25 meter, minus f, which is 40 hertz, times time. So this is our wave function. And then for letter D, we calculate the maximum acceleration A max. Now in our previous discussions, we have A max is just equal to plus minus omega squared A. Okay, so this is equal to plus minus omega squared. We have omega equals 2 pi, the frequency, which is 40 hertz. This will be squared. And then we have A, which is 3 times 10 to the minus 2 meter. So we have A max equals, it is approximately 1,900 or 1,894.96 meters per second squared. So the plus and minus sign gives us the direction. So this is the magnitude of the maximum acceleration, 1,894.96 meters per second squared. So for the next problem, we have a piano wire with mass 3 grams and length 80 centimeters, which is stretched with a tension of 25 newtons. A wave with frequency 120 hertz and amplitude 1.6 millimeter travels along the wire. Calculate the average power carried by the wave and what happens to the average power if the wave amplitude is halved. So we are given with the mass, which is equal to 3 times 10 to the minus 3 kilogram. We have the length, which is 80 times 10 to the minus 2 meter. And then we have the tension F sub t, which is equal to 25 newtons. We are also given with the frequency of the wave that is traveling along the wire, so that it is equal to 120 hertz, and it has an amplitude of 1.6 millimeters, or that is equal to 1.6 times 10 to the minus 3 meter. So first, we have to calculate for the average power. So P average is equal to 1/2 times the square root of mu times F sub T. We have omega squared A squared. Now, we are not given with the value of mu as well as omega, so we can find it through this equation. So mu equals mass over length. We have 3 times 10 to the minus 3 kilogram divided by the length, which is 80 times 10 to the minus 2 meter. So we have mu equals 3.75 times 10 to the minus 3 kilogram per meter. And then we can also get omega through this equation, 2 pi f. So we have 2 pi multiplied by the frequency, which is 120 hertz. So we have 240 pi radians per second. We substitute all the values. We have P average is equal to 1/2 times mu is 3.75 times 10 to the negative 3 kilograms per meter multiplied by the tension, which is 25 newtons. And then we have omega squared, 240 pi radians per meter squared. And then we have the amplitude, which is 1.6 times 10 to the minus 3 meters squared. So we have P average is equal to 0.223 watt. Okay, now we are asked to describe what happens to the average power if the wave amplitude is halved. So we have this initial power. We can call it P sub 1 average. Okay, so we have P sub 1 average corresponding to A sub 1, where A sub 1 is equal to A, and then P sub 2 average with amplitude A sub 2, where A sub 2 is equal to A over 2. So we have P2 average is equal to 1/2. Say for example, we still have the same value of U and F as well as omega, and 1/2 of the original amplitude this time. So we have P2 average is equal to 1/2 multiplied by mu times F sub T omega squared, and then this one is A squared over 4. So from here, we can see that P2 average is just equal to 1/4 of 1/2 mu sub F sub T omega squared A squared. So this expression in the bracket is just equal to P sub 1 average, or we can just write this as 1/4 of P sub 1 average. Meaning to say, when the amplitude is halved, the average power will be quartered. Now for problem number 9, by measurement, you determine that sound waves are spreading out equally in all directions from a point source, and that the intensity is 0.026 watt per meter squared at a distance of 4.3 meters from the source. What is the intensity at a distance of 3.1 meter from the source? And how much sound energy does the source emit in 1 hour if its power output remains constant? Okay, so for this problem, we make use of the inverse square law for intensity. So we are given with I sub 1, which is equal to 0.026 watt per meter squared. And this corresponds to R1, which is equal to 4.3 meters. And then we are asked to find I2 for R sub 2, which is equal to 3.1 meters. So for letter A, we can use this equation, I sub 1 divided by I sub 2 equals R sub 2 squared over R sub 1 squared. Or we have I sub 2 equals I sub 1 multiplied by R sub 1 squared over R sub 2 squared. So we have 0.026 watt per meter squared multiplied by R sub 1, 4.3 squared divided by 3.1 squared. So this is equal to 0.05 watt per meter squared. And then for letter B, we are asked to find the energy emitted in 1 hour if its power remains constant. So from the definition of power, power equals I times the area. So we have I sub 1 multiplied by 4 pi R sub 1 squared. So this is equal to 0.026 watt per meter squared multiplied by 4 pi, or R sub 1 is multiplied by 4.3 meters squared. So we have power is equal to 6.04 watts. Okay? And from the definition of power, power is also equal to energy per unit time. So energy is equal to power multiplied by the time. So power, we have 6.04 watts multiplied by the time. We have 1 hour, that is equivalent to 3,600 seconds. So the energy it emits is equal to 21,744 joules. So we have watt second, where watt is equal to joules per second multiplied by second, so we have joules. Now, problem number 10. The wave function of a standing wave is given by this. Y of xt equals 4.44 millimeter sine 32.5 radians per meter x sine 754 radians per second t. For the two traveling waves that make up this standing wave, find the amplitude, wavelength, frequency, wave speed, and the wave functions. And from the information given, can you determine which harmonic this is and explain? Okay, first we are given with the wave function. So we have y of xt, which is equal to 4.44 millimeter sine, we have 32.5 x sine 754 radians per second t. Okay, now recall that the general form of our standing wave function is we have 2a sine kx sine omega t. Okay, so to find the amplitude of the two traveling waves to find the amplitude for the two traveling waves that make up this standing wave, we have amplitude equals ASW divided by 2. So what is ASW? This is equal to 4.44 millimeters. So we have A equals 4.44 mm divided by 2. This is equal to 2.22 millimeters. So that is equal to 2.22 times 10 to the minus 3 meter. And then for letter B, we are asked to find the wavelength. So the wavelength is directly related to k, the wave number. This is equal to 2 pi over lambda. Lambda is just equal to 2 pi over k, where k is equal to 32.5. So we have 2 pi divided by the value of k, 32.5. This is in radians, and then this one is radians per meter. So we obtain lambda equals 0.193 meter. For letter C, we are asked to find the frequency. So the frequency is just equal to omega over 2 pi. So we have omega, which is 754 radians per second divided by 2 pi radian. So we have frequency is equal to 120 hertz. And then for letter D, we are asked to find V. So V can be obtained by either of this equation, lambda f or omega divided by k. So let's try to use this, omega over k. So we have 754 radians per second divided by the value of k, which is 32.5 radians per meter. So we have 23.2 meters per second. And then for letter E, we are asked to find the individual wave functions of the incident and the reflected wave. So if the incident wave is y sub 1 equals a cosine kx, say, plus omega t. So if this is the incident wave, then the reflected wave is equal to negative a cosine kx minus omega t. So this one is traveling in the positive x direction, while the reflected wave is traveling in the opposite direction. Now, from the information given, can you determine which harmonic this is? So we only have the frequency, the wavelength, omega, k, we have v, but we are not given with the length. So since L is not given, we cannot determine which harmonic this is. So for our last problem, one string of a certain musical instrument is 75 centimeters long and has a mass of 8.75 grams. It is being played in a room where the speed of sound is 344 meters per second. To what tension must you adjust the string so that when vibrating in its second overtone, it produces sound of wavelength 3.35 centimeters? And what frequency of sound does this string produce in its fundamental mode of vibration? So, for a string that is fixed at both ends, we have F sub n equals NV over 2L, where n equals 1, 2, 3, 4, 5, and so on. So here we are given with the following. So first is the length of the string, which is 75 times 10 to the minus 2 meters. We have the mass, which is equal to 8.75 times 10 to the minus 3 kilogram. And then the speed of sound in air, V sound, which is 344 meters per second. And we are asked to find the tension so that when vibrating in its second overtone, it produces sound of wavelength 3.35 cm. So for letter A, we are asked to find the tension so that lambda is equal to 3.35 cm. And take note that this is for the second overtone. That means n equals 3. Okay, so from the given, we can find f sub 3, which is just equal to v over lambda. So v is equal to 344 meters per second divided by 3.35 times 10 to the minus 2 meter. So this is equal to 10,268.66 hertz. We can also find lambda sub 3. So lambda sub 3 is just equal to 2L over 3. So from our definition of lambda, we have lambda sub n equals 2L over n, where n equals 1, 2, 3, and so on. Okay, so we have 2 times the length, which is 75 times 10 to the minus 2 meter, divided by 3. So this is equal to 0.5 meter. Therefore, V is equal to lambda 3 times f sub 3. So we have 0.5 meter multiplied by f sub 3, which is 10,268.66 hertz. So we have V is equal to 5,134.33 meters per second. Now to get our f sub t, we have mu times v squared. So this is equal to m divided by L times v squared. So where m equals 8.75 times 10 to the minus 3 kilogram divided by the length, which is 75, 0.75, okay, 0.75. This is meter. So we have multiplied by the obtained value of V, which is 5,134.33 meters per second squared. So we obtained F sub t is equal to 307,549 Newton. And then for letter B, we have to find the fundamental frequency. So what we know is f sub 3. And we know that f sub 3 is just equal to 3 times the fundamental frequency. Therefore, f sub 1 equals f sub 3 divided by 3. So f sub 3 is 10,268.66 hertz. We divide this by 3 to obtain the fundamental frequency, which is 3,422.9 hertz. So thank you so much for watching.